Hi guys, welcome to our channel of Sciences and Mathematics. I'm Ernest. Today we're going to look at one of the concepts under the configuration and conformation of our molecules, and that is the Kern-Ingold-Prelog system. Now this is a system that assigns absolute configuration to molecules, and of course in our nomenclature of organic compounds, the names that are derived from the parent alkane series and then the prefixes. So in this case, we're going to look at some of the letters which are used in order to allocate or assign configuration to names. And this basically deals with the concept of geometry of organic molecules. So without further ado, thank you and welcome. So our topic for discussion for today, the Kern-Ingold-Prelog system. As I've said, is one of the ways in which we can be able to identify organic molecules, bearing in mind that we have to know their configuration or different orientations of the substituents in that particular molecule. To a molecule, and that basically is under the broader topic of molecular geometry. But for today, the Kern-Ingold-Prelog system is going to assist us identify some of the initials that we had written during nomenclature of organic compounds for R and S, which we said we can be able to allocate a name for R and S, an initial for R and S. And this is basically, these are Greek letters that stand for rectors. And the second one stands for sinister, which basically refers to right. And this one, left. So basically, in trying to assign these specific letters for naming of some of the compounds or molecules, we're going to see that they have specific rules that we have to follow in order to name those particular molecules. Now, first we're going to look at the concept of, in summary, of the enantiomers and chilarity that we have already discussed in some of our videos in organic chemistry, and that is the concept of configuration of molecules and the different substituents, and how we can be able to name a molecule as either an enantiomer or isomers and the stereoisomers. So in this case, I've talked about the concept of enantiomers and the chirality. So I'm going to put a link of the detailed description of this particular concept in the description box below, because we have already discussed about this specific concept in one of our videos. So I'm just going to give a summary of what basically we require to understand in order to understand this specific configuration or assignment of configuration of organic molecules. Now suppose we have a molecule like the one I've illustrated. Let's call this one A and B, and this one represents a mirror line, which basically implies that this molecule has been reflected. B is a reflection of A. So therefore we can be able to call this one object in quotes, and this is the image. Whenever we're trying to talk about the concept of enantiomers and chirality, we can see that the first compound is analogous to the structure of this one. This is analogous to the structure. I don't know whether it's perfect, but I'm just using those strokes. It's analogous to the structure of methane. I just use this hash and then a wedge, and then this specifically. It's analogous to the structure of CH4, which is a tetrahedral structure. So when we try to have this particular molecule represented as this, and then this one is going to form a mirror image of this specific compound. Now there are different substitutional levels that we can have for this specific molecule of methane. Now, and this we can have different substituents. For instance, a chloro, a bromo, methyl, and then this is a 3, and maybe we can have another compound, or maybe let's just say this one can be this is a bromo, chloro, maybe an amine group or something like that, but a different. Whenever a molecule has got different substituents, we can be able to have a general representation for these different substituents for these specific groups as X, Y, Z, and W. So whenever a molecule has got 4 different substituents that are indicated on the board, like this one, this molecule is not going to be superimposable on its mirror image, which basically means that these are going to form 2 different compounds, and therefore I mean a molecule that or a compound that forms a structure like this and is not superimposable on its mirror image is known as an enantiomer. So basically that's how we defined an enantiomer, and we said that for enantiomers the results were never a tetrahedral molecule like the general one that I've illustrated on the board. It's bonded to 4 different substituents, as I illustrated for the X, Y, Z, and W. So therefore, I hope we have understood the examples, or maybe the concept of an enantiomer. We can basically give a specific example for an enantiomer. Now, suppose we have a carbon that has got 4 different substituents, whereby we have a hydrogen, metal, OH group here for alcohol, and a carboxylic acid group at these specific points. The substances are different, and therefore we can regard this particular molecule as an enantiomer. So when an enantiomer has been formed, it has got what we call this central carbon that is here. Now this central carbon is referred to as a stereogenic center, or a chiral center. Can be as well regarded to as a chiral center or a stereogenic center in that matter. Now we're going to see that most of the compounds that you come across, especially under the topic of proteins and carbohydrates, we're going to see that most amino acids, which are the building blocks, have chiral centers. For example, the proteins that I've talked about, most of them consist, which are the compounds that have got amino acids and the building blocks consists of chiral centers. Now we're going to talk about also the concept of a plane of symmetry, and we can see that some of the molecules we can have maybe an hypothetical middle, whereby if we make a plane of symmetry through the center of the molecules, we are going to have objects that forms a mirror image. Now we're going to see that these specific molecules that have got a plane of symmetry do not entail the concept of enantiomers, so therefore they are not, or maybe we can say that these specific molecules that contain this plane of symmetry are not chiral. From this concept of the chirality that we have talked about, using this specific example. Now, if a compound is not chiral, then we refer to that compound as a chiral. Maybe we can just have a few examples from that. Just to go away with this. So I'm explaining the concept of chirality now that we have talked about what an enantiomer is. So suppose we have a compound like the CH, this one is not legible, like the CH 3C H3 CH2 CH2 CH3, and then we have a H here. This is going to form a stereogenic center, and therefore this compound is chiral. And then we can have another compound, maybe there's a substitution for, this is a CH2, and then we have the CH2 OH. This is a stereogenic center, therefore we can regard these 2 compounds as chiral. Now suppose we have a different compound that is got maybe we can compare one of the cyclic compounds that we've talked about in nomenclature. Now suppose we have a compound that is represented, sorry for that. We have a compound that we can be able to represent like this, which has OH, and then that one. Now this one has a plane of symmetry, and we're going to compare it with another compound, this one, HOH. Now if we try to look at the first and the second compounds, we can see that the first one has a plane of symmetry, and the second one, this one has no plane of symmetry. Therefore, the first one can be regarded as a chiral, while the second one is a chiral compound. Perhaps we're going to talk about this concept in a different video, so I just going to reserve it for that so that we cannot deviate further from our topic of discussion for today. So from that one, we are going to look at some of the ways in which we are going to represent this the Karl-Engel-Prelog system, and some of the rules that we are going to assign to this. Now that we have talked about different substitutional, different levels of substitution for an example of a molecule like methane, whereby the H groups, which are CH4, all the H groups have been substituted by different substituents, or maybe the one H is remaining, therefore that is going to form an enantiomer. Now there are specific rules that are used for this absolute configuration or naming of chiral centers. Now that we have understood the concept of chirality and enantiomer, there are specific rules that are used to name these chiral centers, which is an absolute configuration of the R and S that we have mentioned, which stands for rectus and sinister from the Greek words. Now these specific rules are the ones that we call the Karl-Engel-Prelog system, and we will see that the rules give absolute configuration for each chiral center within a compound, and the centers are named chiral centers are given absolute configuration of R and S. So to name these specific centers, there are some specific rules that we're going to mention, which are used to identify these specific stereogenic centers. So the first rule is that whenever we're trying to name this compound, we have to identify a carbon with the 4 different groups attached to it. So therefore, it's identification of a stereogenic center that we have used, the carbon that we have used that is there. And number 2, we're going to put the lightest group at the back, which is pointing away. So in this case, the lightest group is the group that consists of the lowest either atomic or molecular mass. So this group is it is put away. Just going to put this one so we're going to put it away from that. We're going to look at the geometry of that particular orientation, so maybe the orientation of that particular molecule. So and that is given, of course, going to see the priority is given. So the rule number 3 is that we give the heaviest group attached to the heaviest priority. So with respect to this particular mass, molecular mass or atomic mass, we're going to give the heaviest group is given the highest priority, And in this specific case, we're going to use the numerical figures, for 1 being the highest priority and the preceding numbers in that order from the low to the lowest. And then we're going to see that we're going to give the third heaviest group attached number 3. So this one goes in that order, whereby number 1, the priority number 1 is given to the heaviest, and then number 2 up to the lightest of those specific substituents. Now in this case, then the lastly, we're going to be given a condition whether to determine whether a molecule is an S, or a stereogenic center is an S or an R. That is for that configuration, whereby if the lightest group or the atom that is pointing away that you said, and then the highest priority is given to the heaviest, as we have said, and then if that sequence of numbers, as we have said, we are going to have a orientation whereby this is going to form the center, which is a stereogenic center. Say for instance, this is a carbon with the lightest group pointing away from this, and then other, of course, molecules. Let's say this is a nitrogen. It's a nitrogen. Let's give just like a chloro, maybe a bromo. And if and then this may be an OH. If the lightest group is pointing away, then we're going to consider the molecular masses, maybe the atomic masses of these specific constituents, and see which is the lightest. Now suppose if the trend of allocation of numbers for priorities, it's number 1, 2, 3, then along this, the lightest pointing away from the observer, then we're going to see that the trend is going to go in a specific way, which we can be able to regard either the clockwise or anti-clockwise direction. And the one that goes clockwise, the center is named as an R, and the one that goes anti-clockwise, the center is named S. So we're going to give that illustration using examples that I'm going to, of course, draw on the board. So just do away with this. So I'm going to give an illustration of maybe 1 or 2 molecules, and so that we can give them as examples. Now, I've given 2 specific illustrations for comparison. Let's call the first one as A and the second one as B, whereby A encompasses this one and this molecule, and B this one and this one. So we're going to start with A, and we have said that the lightest molecule, or maybe an atom, is going to point away from the observer. So therefore, this is the point from which we are trying to view this molecule. Then we are going to consider this specific 3 substituents in order to see which one has the highest priority in terms of maybe allocation of atomic or molecular mass, whereby this nitrogen has got 14 plus 2. So let's try to consider the atomic or molecular mass of those specific substituents. Now this one has got this is 14 plus 2, this is 16, and this is 12 plus 3, 15. So therefore, the nitrogen one is going to be heavier than that one, and we are going to have this specific molecule. Now for fluorine, if we try to look at the periodic table, that is going to be heavier than this other. So we're going to have that one as 1, 2, and then 3. So we have given the heaviest the first priority, followed by the second and third, and therefore from that particular configuration, we are going to have the priority moving from number 1, 2, and 3, and this position is a counter-clockwise. And for this one, fluorine is still going to be number 1, and then we're going to have number 2 for, that is amine group. is 14 plus 2, 16, this is 12 plus 15. So this is going to form number 3. So the numbers I'm calculating is for the total of molecular mass of that particular substituent. So therefore we're going to have this one, the priority move in that direction, and this is the clockwise direction. So now for the counterclockwise direction, we allocate S, while for clockwise direction we allocate R. So therefore, whenever we're trying to name those molecules, we're going to allocate F and S and R using those priorities. So first, you have to identify the stereogenic center from the procedure that we have talked about. And number 2, you put an orientation to that molecule in a sense that the lightest substituent always points away. And then from this, you can be able to allocate the priorities starting from the heaviest group being given the first priority, and then the second heaviest, going in that specific order up to the second, lightest from that specific order. So whenever we have achieved that, then we can be able to see the specific orientation for clockwise and anti-clockwise for those specific molecules. Now for counterclockwise, we have said it's given an S, and the clockwise it's given an R. If we consider the below molecules, we can see that the first one, which basically if we find it as an object and then an image, this image is not superimposable on its a specific molecule which forms an object in quotes, as I've said. So therefore we can be able to regard the just 2 illustrations, bearing in mind that this one is an hypothetical mirror line, as enantiomers. Therefore, from those enantiomers, let's try to see the priorities which we can be able to use in locating the priorities. So from this, we're going to see that we are going to assign number 1 to bromine, and then 2 for chlorine, and lastly for bromine, bearing in mind that the lightest has faced away from us. So we're going to have that orientation according to the priority moving in that direction, and therefore that one is a counterclockwise, and we're going to give that one an S. So this is an S enantiomer, while if we try to look at at the same time for the substituents of those ones, which is a mirror image, still we're going to give this one number 1, fluorine number 2, fluorine number 3, and in our case here we're going to have a moving clockwise direction according to those priorities. Therefore we are going to give this one an R enantiomer according to those rules. So we have identified the stereogenic center as this one. We have put the lightest, of course, substituents away from us using that those hash. That's hash indication, and then we have a wedge. This is pointing towards us, away from us, along the plane of the board. So this is pointing away from us, towards us, along the plane of the board. So this is pointing away from us as the first rule, as the lightest. Having identified the stereogenic center, now using the molecular masses, we have been able to allocate the orientation of those molecules by identifying, using the numerical letters, whether it's moving clockwise or anti-clockwise, and that's how we can be able to identify whether that molecule is an R or an S, and therefore giving it an absolute absolute configuration that is referred to as the Kahn-Ingold Prelog system of trying to name, just basically naming those stereogenic centers. Now I hope that this one, compounded with the other discussions that we're going to have, especially on drawing of three-dimensional illustration or molecular structures, is going to give us an insight on how we can be able to identify different molecules, and basically the concept of molecular geometry and others are going to assist us in order to maybe try to figure out how we can be able to identify this molecule. Now, having illustrated this is specific hashes, the wedges, and then just the lines, and mentioned that maybe these lines are just along the plane of the board away from us, and this one. This basically is going to find a broader explanation in molecular geometry, or maybe drawings and representation of molecular structures. But for this one, I hope that we have understood how the Khan-Ingold parallel system of assigning chiral centers works, and we are going to use these specific examples in trying to solve problems that may come along our discussion, which are basically related to this one, either directly or indirectly. So for that case, I hope that the topic is clear. And kindly go to our YouTube channel and subscribe so that you can be getting updates, and we try to relate different aspects and concepts that we are discussing in mathematics and sciences. So that is it for today. I hope that you have achieved something. Thank you. Bye. God bless you.